case. Please, you're welcome.
Okay. Ну, спасибо за приглашение. Для меня огромная честь быть на этой конференции. И спасибо за возможность так представить эти вместные результаты с Владимиром Драговичем и Božidarom Jovanovićem. Ну, I will pass to English. I will present. So, here I will present this is joint result with Vladimir Dragović, Božidar Jovanović, and this is gyroscopic Chaplygin system and generalized Demchenko case. So, here is this year is exactly 100 years anniversary of PhD thesis of Vasily Grigorievich Demchenko, and the PhD thesis is written in Serbian. This is rolling of gyroscopic ball over the sphere. Then this is University of Belgrade in 1923, and you know, when it after the revolution in Soviet Union in Russia, there is a lot of people came to Serbia, a lot of immigrants, and then they gave a very big influence in Serbian science, Serbian culture, and among them there is Anton Bilimovic. He was director of University of Odessa before that, and then came to Serbia, and then he met in Serbia at that time was Mihailo Petrović, that is very famous and very prominent Serbian mathematician, and also there is Milutin Milanković, and they form a very nice group in mathematics and classical mechanics. And but one of the students they came in Subotic, in north part of Serbia, was Vasily Grigorievich Demchenko, and he was I think that he was student of Petar Voronets. Petar Voronets is very close friend and collaborator with Anton Bilimovic, and Petar Voronets also came to Serbia, but on short time. Then after that, he went back to Soviet Union, and then after that he died in, I think, in 1924, 1925, something like that, and. But Vasily Grigorievich Demchenko started to study non-holonomic system with influence on the Voronets, and he finished his PhD thesis with his advisor was Anton Bilimovic. So after that, he went to Paris, and 4 years later, in 1928, he finished his second PhD thesis. Second PhD thesis was in fluid mechanics, and after that he worked in fluid mechanics. He has some monographs and papers and so on. But recently we found this PhD thesis. It was completely unknown because of course, it is written in Serbia 100 years ago, and there is fortunately they recognized at that time that is a very good thesis, and it is published by Serbian Royal Academy of Science and Arts in 1924. So this is rolling off without sliding off gyroscopic ball over the sphere. Okay, so. Now our idea is to study in more general case, more general framework with non-holonomic systems with addition of gyroscopic forces. So let us start with we consider non-holonomic Lagrange systems with gyroscopic forces. So we have Q is the manifold of configuration space of our mechanical systems. G is Riemannian manifold given by kinetic energy, and we have one. It is usual that Lagrangian system is kinetical minus potential energy, but we have that. Let us suppose that we have Lagrangian L1. We have in addition we have this linear in velocities. So A is one form on Q simply. So. We will say that the equation of motion of this system can be given by using Lagrange-D'Alembert equations. So they're given here, where the delta Q, this is the virtual displacement, there belongs to the non-integrable distribution. I forgot to say that non-holonomic system, this means that in tangent space, in tangent bundle of TQ, in any point you have you have the subspace, so that gives us a non-integrable distribution. Non-integrability of distributions exactly means that we have non-holonomic systems, so that this is mechanically this means that one has the constraints linear in velocities. Okay, so this equation of motion from the Lameller equations, one can see the equivalent way if we have standard Lagrangian, then in standard Lagrangian, the equation can be written by this form, where we have addition. In addition, we have this is additional force, but in this special case, when we have this linear part in Lagrangian, one gets that F is dA, so simply means that F is in coordinates, say, given by this is linear in velocities and given by skew symmetric matrix. But this is exactly the differential of this one form A. But our idea is to consider more general case where the additional force is given by two form, which is not close to not even exact. Okay, so and we'll call that this QLFD is natural mechanical non-holonomic system with gyroscopic forces, and here L is given Lagrangian, is standard because it's a natural mechanical, so Lagrangian is potential minus kinetical energy. If in special case, when dF is equal to 0, when F is closed form, then we will call that system, this non-holonomic system with magnetic forces. Okay, so now let us suppose special that we have that Q, our configuration space has a structure fiber bundle. So we have base manifold S, we have natural projection such that the fibers, the vertical fibers, so that dQ, the distribution is transferred to the fibers of P, transfers to the fibers of P. That simply means that tangent space in any point can be seen as a direct sum of this dq that gives us distribution, and the vertical space, this is kernel of dp. So how it is known in differential geometry, in this when we have this fiber bundle structure, the choice of horizontal space simply means here that the choice of distribution gives us the connection on the fiber bundle. So we'll call it one form A on Q defines Ehresmann connection if it is linear mapping on any tangent space, and this is projection of vertical space. So if we have if you have any vector field on Q can be decomposed in vertical part and horizontal part, and the vertical part is horizontal part belongs to distribution, is projected with A to 0, and vertical part is the rest. Okay, so and why it is usual to consider what is the curvature of the connection. The curvature of connection is defined with this formula. So simply means if you have two vector fields x and y, then take the horizontal parts and find commutator. But since distribution is non-integrable, this vector field is not horizontal, so it has vertical part, and let us project with sign minus to the vertical, to the knee vertical direction. One gets this. This is curvature of the. Okay, so in this case, Voronets use this special case when we have this structure of fiber bundle. So simply means he looked, of course, in local coordinates locally. When we have our Q is dimension of n plus k, we have k non-holonomic constraints, and simply he considered case where Q and the Q dot n+1 to n+k can be find as a linear functions of the corresponding of the velocities q1 dot to qn dot, general velocities. And he developed his Voronez's principle, and from principle he gets this equation of motion, but without these last two terms in red. This is classical Voronez examples, but now because we have additional gyroscopic forces, we have these two additional parts. Okay, so here LC is constraint Lagrangian, so this simply means this is classical Lagrangian, where we imply this we change this velocities qn plus nu with we use these constraints and imply this in classical Lagrangian, then one gets the constraint Lagrangian. And Q here we have this additional part. In our case, we have these additional parts are given by our non-gyroscopic forces. Here, as you can see on the right-hand side, there is Bij nu. It is components of curvature tensor given in local coordinates. And this is classical equation of Voronez without these gyroscopic terms is given by Voronez in 1901, and is this geometric setting it was given by Bloch, Cooper, Kirchner, Prast, Marsden, and Murray in 1996. Okay, now suppose what Chaplygin did. Chaplygin considered more general case where this vibration is no more general, so more specific case. When this vibration is determined by the free action of k-dimensionally group G, such that this quotient manifold S, we have this quotient, these orbits, and with condition that all objects, so distribution, the gyroscopic two form and Lagrangian are G invariant. Of course, he considered a case without a gyroscopic term. Now we consider with these two form, when we suppose that this gyroscopic two form is G invariant, and then A is principal connection to the non-coulombic system is G invariant, and one can show that the equation of motion can be reduced to the base manifold, to the tangent bundle of the base manifold. In this case is S. So in special case, when we have this action of Lie group, one can reduce the equation of the tangent bundle of S, and there is equations. Just this is how they look, and this term JK JK term is it is not visible here, but this term is given by condition that D is non-integrable distribution. So this is part that exists because of non-integrability of D, and it depends on the metric and curvature of the connection. And this red part, this additional part, is exists because of this gyroscopic force. And this, without gyroscopic forces, Chaplygin considered it in 1911. He considered where G is in abelian group. This is, and then it is for arbitrary action of Lie group G. It is given by Euler in 1992. It is very important references in the subject. But now here we have this F, this additional term given by gyroscopic forces. Okay, so in this setting we call the reduced gyroscopic G Chaplygin system. This is projected. The system can be projected on this tangent bundle of S, and if the case is small, projection of the small f is now projection of the gyroscopic forces to the S. So then we talk about reduced. In case F is closed form, we talk about reduced magnetic G Chaplygin system. And it is very interesting that if capital F is closed, F not need to be closed. But if for example, if D is integrable distribution, then then this is automatically satisfied. The f is closed, the small f is again closed. Okay, and of course the solution Chaplygin system project on the solution of the reduced system, and if we have a solution of reduced Chaplygin system, one can lift it to the solution of gyroscopic Chaplygin system on the Q. Okay, so we know that in the case of non-holomorphic system, they are not Hamiltonian, but so now let us suppose on this S project on the reduced space, if we have local coordinates in this metric, then let us define the C is 1 to 10 with this formula with sigma. Sigma is, if you remember, given by this this term in these equations. This depends on curvature and connection. This is 0,3 tensor, and now we have using metric one made this 1 to tensor C. If we have classical, we have classical on tangent or cotangent angle of S. One can then canonical way how to find. We have Hamiltonian function and usual Legendre transformation, and one gets then the reduced equations can be written in this form, and this term, of course, these systems, these equations are not Hamiltonian in canonical structure. So we have this term pi. This is given by this formula. So this pi is part which is given by non-holonormity of the constraints, and we have in addition this third part is given by our gyroscopic forces. Okay, so the reduced equation can be written in almost Hamiltonian form. So this simply means that omega is canonical symplectic form, but this is Demchenko first proof that in the case of non-holonomic system, if one adds the sigma, then one gets the form omega plus sigma. This is not closed, so this is reason. That's the reason why it is called the almost Hamiltonian form. But here, in addition, we have this part which is given by this gyroscopic forces. Rho is a canonical projection from cotangent space S to the S. Okay, so natural questions when the reduced gyroscopic Chaplygin equation have the invariant measure with density Q, and we have that this theorem that it is satisfied if and only if the one form is exact. Then the function is density of the invariant measure. Okay, so now the natural question what was given by first by Chaplygin, he considered when we have in Lagrangian form our equation of non-holonomic system, is it possible to change the time so that to find some function n such that after changing of time in new time after time representation this equation can be reduced to the classical Lagrange equations where L star is L, but given in new coordinates. Instead of x dot, it is given with x prime. So this. So, okay, so let us consider G Chaplygin system with gyroscopic term. This form is conformally symplectic. We will say that this form is conformally symplectic if there is function n such that when we product this form with n, we have closed form. So this is condition, equivalent condition, this formula, and one gets that now we have additional. So the function is conformal factor for almost symplectic form given by this formula if and only if it is conformal with almost symplectic form without this gyroscopic terms, and this form n times f, this f star is closed. It is closed. Yes, it is magnetic. then the reduced equation can be written in this form, Hamiltonian form. So after that, on the other hand, let us consider the case of a Chaplygin multiplier. It's given by here. You see that it can be Lagrange, and then pass here. Let us pass using Legendre transformation to the cotangent bundle of S. Then introduce this is pi sigma. This is dl star over these new velocities. And then there is corresponding Hamiltonian, and we see that we have this commutative diagram. So if we have a Chaplygin multiplier to pass from Ts to the again in new time to the system, and then make the Legendre transformation, it is the same as first do Legendre transformation and then use this change that P sigma is equal n times P. So now tilde is canonical symplectic form of T star S with respect to these new coordinates X and P tilde. So given this formula, so now and assume that our D2 form is closed on S. This is exactly the case that we discussed before here in case of proposition. The function as a Chaplygin multiplier if and only if the almost Hamiltonian equation after time reparametrization become this Hamiltonian equation, but with respect to new, this is twisted symplectic form. We have this canonical symplectic form with this in after time changing, but we have this additional term given by n times defined by our gyroscopic forces. So we have that n is Chaplygin reducing multiplier for the reduced Chaplygin system if and only if this C satisfies this equation. So but in invariant form, this JK, this is P. This is term in this Hamiltonian, if you remember. Let me show you again. So this is P. This P depends of the curvature of the connection. So if P has this form, it is clear that sufficient condition, of course, is that CID is given by this formula. Then the C12 tensor C and two forms sigma is invariant form can be written in this. This is formula 4 and 5. And generally speaking, after we have this theorem, this is retrospective of what we present. So we have that C is 5, A, B, and C are mutually equivalent, D and E are mutually equivalent, and from D or E, it follows one of the A, B, and C. So what is we have that reduced Chaplygin system after the time reparametrization takes the form of the magnetic Lagrangian system. This is equivalent to that reduced gyroscopic Chaplygin system after time reparametrization, and the change of variables take the twisted canonical, take the Hamiltonian equation in the twisted canonical with respect to the twisted canonical form, and that this P term or cotangent bundle has this specific form too. And the almost symplectic form is conformally symplectic with the base conformal factor n, based this function on x, and sigma is given by 5. This is equivalent that C has this formula 4. And what is very important that when we have Chaplygin multiplier, then the reduced equations of motion, we know that non-polynomial systems do not has invariant measure, but when we have Chaplygin multiplier, then the reduced equations possess the base invariant measure. This is given by this is n on n-1 times omega n. This is standard measure in on S. in special case n equal to 2, then then this means that after time change, the equation became the usual Hamiltonian equation of cotangent bundle of S. Okay. Now let us pass. I have, I think, 15 minutes. Let me try to give just what is our main example. So let us consider rolling of a ball over the sphere. So we have sphere, we have ball. Sphere is fixed, ball is moving over the sphere, such that in the point of contact there is no sliding. So this gives us our non-holonomic constraints, and the sphere has radius small b, and the ball has a radius small a. Then, and let us suppose that the operator of inertia of the ball, so the ball is generally the dynamically non-symmetric ball, but it is balanced. This simply means that the geometric center coincides with center of masses. And then we have that operator of inertia has on diagonal, this diagonal form, because one can choose the principal coordinate system, and this is A, B, and C are principal moments of inertia. Okay, now this is system. This is considered. Okay, so now let us assume that we have the gyroscope. The gyroscope is placed in the ball B such that mass center of the system coincides with the geometric center. So and we consider this case in 3 possible configurations. So we have ball over the sphere, ball inside the sphere, and there is ball. Ball is out of the sphere, ball is inside, and here is ball over the sphere. This is so-called spherical shell. So all 3 configurations can be together considered. So let us consider epsilon is b over b plus this is parameter, b over b plus a in the first case, and b over b minus a in the two cases. So this is the problem. Without gyroscope, it is considered, it is by Borisov Mamayev, and there is also Borisov Fyodorov first proved that this system is integrable without the gyroscope. Only in case, they found the case when epsilon is equal to -1, which corresponds to the third case, one gets the integrability. But for other epsilons, probably there is no integrable cases. No, there is no, there are no other integrable cases. When epsilon equal to 1, see that this sphere goes to radius of b goes to infinity. When b goes to infinity, then one gets the rolling of ball over the plane. So in rolling of the plane without gyroscope, this is system considered by Chaplygin. He proved its integrability, but with gyroscope, it is proved by Markeyev recently. Okay, so the addition of gyroscope is equivalent to addition of constant angular momentum that is directed along the axis of the gyroscope. This is then the equation of motion can be written in this way. So they here k, this k is given by this formula. This is angular momentum with respect to center masses with some additional term, and this constant, and this kappa is constant angular momentum of the gyroscope in the body frame. Okay, so in the case epsilon equal to 1, I already said that the motion of rolling of the plane, Markeyev proved that can be doing in quadratures. It's given by this formula. But before that, it was first when there is rolling over the plane. In special cases are considered by Bobilyov in 1892 and by Zhukovsky in 1983. There is famous Bobilyov and Zhukovsky cases. The Bobilyov case, he considered that the central ellipsoid of inertia is rotationally symmetric, and the gyroscope axis coincide with axis of symmetry. Then the operator of inertia has this form AAC, where and the kappa is constant along the axis of symmetry. And he proved the integrability of the case. And Zhukovsky case has additional assumption. This is Zhukovsky case where the C1 it is more. Let us consider when C1 is A1 plus A2, then it is assumed that T is proportional to identity matrix, and he also construct this system. He gave a way how to construct this system, and he proved that this system can be resolved in elliptic functions. Now, the question that is considered Demchenko, he is considered the using. This is so Zhukovsky considered the rolling of ball over the plane, and then in 1923, the Zhukovsky conditions for rolling over the ball over the sphere with this in this condition, the Zhukovsky conditions was considered by Demchenko in 1923. This is the main problem considered by Demchenko. The integrability of problem rolling of gyroscopic over the sphere with Bobilyov conditions was proved by Borisov Mamayev-Kilin in 2005. And the question about existence of integrable case for dynamically non-symmetric ball, it is still open up to our knowledge. Now, but this system is not G-Chaplygin system. Let us consider the case when we have additional, this is non-twisting condition. So that omega scalar product with gamma is equal to 0. So simply means that the omega angular velocity of this ball has no component in direction, it's just orthogonal to the sphere. So there is no twisting, and this is now in equation one gets we have this additional term, and now k is equal to E omega, and in this case, one can prove that this system is SON invariant, and that can be, we have action of SON group, G is SON, and one can reduce the equation to the cotangent bundle of the sphere. So we consider the generalized Demchenko case without twisting. So Demchenko considered with twisting. It is possible twisting. Now, let us suppose that there is no twisting, and the generalized Demchenko case without twisting. Now, in arbitrary dimension is system of balanced n-dimensional gyroscopic ball rolling without slipping over the n-1 dimensional space with the additional Zhukovsky condition that inertia operator is proportional to the identity operator. So, in this case, one has that equation of motion. This is equation of motion can be reduced to the magnetic the cotangent bundle of the sphere given by gamma is equal to 1, and the equation are the magnetic geodesic flow of this Hamiltonian with respect to the magnetic Poisson bracket. So we have this is equation of motion, and their Hamiltonian with this with respect to this Hamiltonian with the magnetic Poisson bracket given by these formulas here. So okay, so there is cotangent bundle of sphere. Znači, okay, so this is equation. This is the equation of motion. Now, I will in three-dimensional Demchenko case, this is equation, and one can prove. We proved that this reduced equation they are integrable in quadratures, but I will pass only for the four-dimensional case. The analysis is for three-dimensional case is similar, or is maybe more interesting case. Now we have our kappa is given by this skew symmetric matrix. kappa 1, 2, kappa 3, 4. This is our gyroscopic momentum. And the reduced equation can be written in this form. We have gamma 1 dot, gamma 4 dot, and this is additional momenta. Mu is this Lagrange multiplier, and there is Hamiltonian of the form. The reduced equation is the Liouville integrable on cotangent bundle of three-dimensional sphere with the three first integrals. This is Hamiltonian, and these two integrals, they are in involution with respect to Poisson Poisson magnetic bracket, and then we prove that this reduced equation can be explicitly integrated in elliptic functions, and of course degenerate. Okay, degeneralizations. So how to integrate the system? Now let us introduce new coordinate. This is so we have S3 is given here in R4 as part of R4. So let us gamma 1 and gamma 2, they are polar coordinates in 1, 2 plane, and gamma 3, gamma 4 polar coordinates in the 3, 4 plane. Then in new coordinates, the first integral can be written this, and we have that phi1 dot can be expressed in this formula, again phi3 dot with this formula, and when one introduce u is rho 1 squared, it follows that u satisfies this equation where the p3 is polynomial of the degree 3. So one gets the u is generally in general situation, this is can be seen as a symplectic as an elliptic function of time. So let us, if we and we found that after this linear change of variables, z is linear in u, one gets that solution can be expressed using Weierstrass P function. And what is we have some qualitative analysis. So let us suppose so for since u is rho 1 squared, it follows that we have motion when u is changed between on interval 0, 1. This is real motion. Then and what can happen? It can happen that P, there is no real roots, there is two distinct real roots and one double root. So if there is no roots, then there is no any motions, no real motions. But in the case 2, when the polynomial has two distinct real roots, then qualitative picture depends on this is some u kappa. So if u kappa belongs to this interval, then we have one regime of motion given by these two formulas, these two pictures. So we have that phi dot can change the sign during motion. So we have this this kind of motion. When u kappa is equal to u2 or u kappa is equal to u1, then we have these situations, and the case when u kappa do not belong to interval, we have this situation, and these similar pictures in three-dimensional case, but with twisting, with possible twisting, are given in Demchenko's thesis also. So we also have some case of double root. We have stationary motion, and there are references. This material, this is part of our paper given by, it's published in 2023 in Journal of Nonlinear Science. And before that, we have in Theoretical Applied Mechanics. This is our Serbian journal, which is published by Serbian Society of Mechanics and Mathematical Institute. We have put some light on Demchenko's thesis because it is completely unknown. Of course, it is written in Serbian, and it is completely unknown to the wide audience. And there are also 3 papers. It's given by this rolling of ball over the sphere. Okay, thank you very much.
Thank you. Any questions? Well, I have a little question because your result looks not just very interesting, but also very applicable. So, is there any applications? What application cases when your model is working?
Well, it's a nice question, but I don't know. We don't know yet about applications, but it will be very interesting. If it is possible to.
I see. Well, I'm a
thing.
fan of monowheels, so it looks like the model of. It looks a little bit like model of monowheel, so perhaps you can improve this mobility systems. Thank you.
Okay, thank you.
The next speaker is